The first tutorial we have seen is for the bubble rising case, where we have captured. So in the first case, we have seen how to capture a bubble interface using VOF method. Now, in the multi-phase itself, there are a few methods which Professor Naren has also captured, called as Eileren two-phase flow model, in which we'll, instead of capturing the interface, we'll only see the bulk effect, which is called as mixture model. So for that, we're going to see the fluidized bed case. Yeah. So we're going to see this fluidized bed case using mixture model. So fluidization or fluidized bed is a process where the bed of solid particle is transformed into something closely resembling a liquid by pumping air or some kind of fluid from the bottom of this channel. The fluid is pumped at a rate at which it is sufficient to exert a force on the particle that exactly counteract the weight of the particle. So instead of rigid structure held in place by means of gravity, the bed acquired a fluid-like property. So as you can see in this animation also, so from the bottom of this, we are pumping the fluid at a constant rate, and because of that, the motion we can see in this bed. So in this, so this bed can be of anything like small particles, sand. So capturing the, or instead of resolving the each and every particle of the sand or drop or some solid particle, we're going to model it and model as a single phase using mixture model. So for which, so here also we can see that instead of capturing a single droplet, we'll average the volume of both the phases and only will able to see the bulk effect of each phase. That means we cannot say that this like in this case, we'll not able to capture a single phase or interface of it, but we'll able to see some bulk effect, like uh, flow through a pipe and flow through pipe is there, and inside the pipe, air and water both are flowing. We'll able to see the bulk effect that okay, in some region air is flowing and in some region water is flowing. So like that only we'll able to see. So for this, so earlier for VF model, we have solved three equations, one for conservation, one for momentum, and third for the volume fraction. But in mixture model, as we are not capturing any interface, so for each phase, we'll solve one equation. So suppose solid phase is there and gaseous phase is there. We are considering it here. So for solid phase and gaseous phase, we'll solve one continuity equation. And again, for solid and gaseous phase, we'll solve uh, momentum equation. Now again, uh, as we are modeling it, so for interfacial momentum exchange, will uh, even earlier also Professor Narendra has introduced in his lecture that for interfacial model we'll use some source term called as drag force, lift force, and virtual force. So for this fluidized bed, we'll only consider this drag force, and in VF model we can calculate the drag force, but in this case, as we are not capturing any interface or not resolving, we're going to model it using some standard models which are already existing in the literatures. So for this fluidized bed, the standard model or drag model is called this Gidaspo model, which will going to model, which we're going to use at as in the as the source term in the momentum equation for the interfacial momentum transfer. And for that, first we'll define what will be our particle size, that is called dp. And based on that, we're going to calculate this drag force. So coming to the computational domain, so again, as we have done it in VF model, we're going to initialize our bed. So this red portion is our solid bed, where we'll define it is not a fully solid bed. Some air, some fraction of air will also be there, and some fraction of solid will also be there. So that we're going to initialize, and from the bottom of it, we're going to pump air, and how it will going to behave, that we're going to see. So So for that, the fluidized bed tutorial is already available in open form. So if you go to open form tutorials, multi-phase, inside multi-phase, there is a name called as multi-phase Euler form. So open this. So we can simply see the laminar one. Uh, you can try for RANS or LES also. So inside this laminar, this fluidized bed tutorial is present. You can copy this.
Hello.
Yeah, hello.
Actually, I want to know means what is the philosophical difference between multi-fluid model and this mixer model? Because in multi-fluid model also we use the same special equation and momentum equation for both the pages. So
Okay.
are they same? Means similar?
Means no. Whether you are
What is the
capturing the
difference
interface
actually?
or
No, in Eulerian or multi-fluid model also, we do not capture the interface. We want to just see the dispersion of the
yes, yes. So
phases.
both are
Means,
same then.
okay, okay. Means the only thing is the difference in applicability.
Yes, yes. Application will only change. So simply copy this fluid model wherever you want to run it. So everyone is able to look at the this fluidized bed tutorial, right?
Yeah.
Okay, fine. Then we can move forward. Okay. So as I've introduced what exactly is fluidized bed and what how we are solving this mixture model. So now we'll have zones it got created. So for not having some confusion, I'm simply deleting these zone identifiers. Yeah. So as you can see, so for each phase, as I've showed, we are solving the continuity and momentum equation. So likewise, for each case, we have to define the boundary condition. So like u particle is velocity of the particle, u air is the velocity of air. Then coming to alpha. So earlier VF model, we are only solving the alpha for one phase, and we are capturing the interface for the other. But here, as we are not resolving any interface, so we're going to solve alpha air also and alpha particle also. So we'll see what are these boundary condition they are using inside this velocity of particle and velocity of air. So as you can see, in velocity of particle, we have not defined any velocity for the particle because it is just a static bed. And because of the fluid motion from the bottom wall, it will going to change or it will show the fluidized nature. But for the velocity of the air, you can see we are giving some constant velocity inlet. And again, uh, for the initialization part, we can see here set field is also given for this case also, so that we can initialize our bed. Yeah. So for the bed initialization, so as this is a solid bed, so some portion of solid will be there, and in the gaps of uh, the solid, air will also be trapped. Right. So default value will be 1 and 0 for the bed and particle. But for defining the that up to certain height only our bed will be there. So it will act as a porous media. So alpha particle we are giving as 0.55 and air we are defining as the 0.45. That means 55% of the bed is covered with particle and 45% of the bed is is having air, and uh, we are defining this as box to cell. That means it is a rectangular box, and the box dimension we are defining it here. Okay, so till here everything is clear, or
So what is the 0.45 and 0.55 values?
okay. So these are the values of opacity. We can say that.
We are defining a box in which we have air and particles also.
Yes, yes. So it
We
is
are not
something like
rigid.
this.
Okay.
No, it is not a rigid one.
Okay.
It is a void fraction. So
I think
till
I think these are initial values of the volume fraction, right?
correct, correct. These are the initial values of volume fraction.
Okay. Okay. Thank you, sir. Thank you.
So now coming to the constant folder. So here, as this is, we're going to model uh, drag and gravity effect. We'll also going to consider. So gravity file is also is there. Now, uh, we have to define the turbulence property for the particles, turbulence property for the air, and what will be their thermophysical property also we have to define. So we'll see one by one. So first we'll see the momentum transport of air. That is nothing but the turbulence properties. So we have selected the laminar case. So as air is a continuous phase, so we are treating it as a laminar. The simulation type will be laminar. But coming to the particle, so what kind of flow it will going to show us? So for this, we are using RANS model, and inside RANS model, we're going to model it using kinetic theory. So inside kinetic theory, so as anyhow we are modeling this solid bed as kind of a continuous fluid, but there will be particle-particle interaction will come, and uh, how you will going to model it as a continuous fluid. So for that, we're going to specify the viscosity model, conductivity model, how the particle will interaction will transform it or translate into pressure, then friction between the particles, all these things will going to model. So there, these are some standard models using which we're going to model it. Uh,
Hello, sir. Actually, I have a question.
yes.
Okay, actually, once I used that Eulerian model. In that case, there was a constraint that I had to use. I had to use means non-zero initial value for all the cells. Means it was very less, maybe of the order of 10 to the power minus 4, but
Okay.
it would not be set to zero. So is it a constraint real for that models?
Not necessary because for which case you are
Means
referring?
can I set to zero physically? Means it is actually continuous phase, means all the phases are continuous, continuously mixed. So zero means physically or mathematically, can it be set to zero?
Yes, sir. Because here also, if you see the default value, I have kept as 0. But if you keep it
Okay,
a
okay.
very small value, that is also not a big deal.
Not required, right?
Not required. Yes.
Okay, okay. Okay.
Yes. Now coming to the phase properties. So as a I was explaining earlier from the PPT that we have to specify the diameter of the particle size. So that we're going to specify it here. So this is our particle size. So currently we have set our particle size as 3 into 10 power minus 4. And in this file itself, we're going to define the drag uh, force, means how we are modeling it. So this is how we are going to specify it. And this is that drag model which we're going to use. So till here, is it fine? We can move forward.
Yes, yes.
Okay then. So now we'll see uh, about running of this case. Yeah. So first we'll create our block mesh. So you can use the same block mesh command. So this is also a 2D case. That's why inlet, outlet, walls, and front and back is coming. And front and back will set as empty. So after this, uh, as we are saying that in multi-phase will initialize some field. So for that, set field command will run. So this will going to initialize our alpha air and alpha particle. Now after initialization, we'll able to see this alpha air and alpha particle. So we'll open any one of this file. So you can see it has initialized because we have given the initialization of particle bed as 0.55. So you can see it has initialized and everywhere the internal field is written as 0.55. And if I'll open the original file, so here it is non-initialized. So after initialization, so as this is not a interface capturing uh, method, so we're not going to use interform. So for such kind of problems, we'll use multi-phase Euler form. So this is the solver for this. So once you press enter, it will start running. So everyone is able to run it, or no, for this CP command is not required. You can directly use set fields. So till here everything is clear. Everyone is able to run it. Okay. So this case also be running for the end time of 2 seconds. It has reached 0.08. It will take time. So for now I will stop it. Uh, I already have one run case. So we can see the post processing of that case. So once you open this in ParaView, go to alpha particle, you will able to see this is our fluidized bed. So once you start running, you will able to see as the air is getting injected inside this fluidized bed, the nature of this bed will start to change because of the air pressure, the fluid bed will get disrupted and it will move up and then it will slowly come down. Now, if you see, after reaching to a certain point, the bed particles start to move or fall downwards, or start to falling. Then this process will continuously go, will be repeated. Because of the continuous pumping of air, the bed particles will go up and then it will come down. No, no, it is different, sir. So this is the fluidides bed case. So this case is given in the open form itself. So if you go to tutorials, multi-phase Euler form. So currently we are simulating the laminar flow. Inside this laminar flow, this fluidized bed case is given. You can follow. You can use this. So now if you see that the bed particles are slowly coming down, and again this will start to it will show the transient process of this bed. So everyone is able to run this case, right? So this kind of fluidized bed is used in the application of suppose you want to dry something or heat up something with non-reactive particles. If you want to heat up or you want to dry it under the influence of hot air or cold air, in that case you can use it, or in chemical industries. So further, you can do the post processing for this also. You can check the
I am still running my this simulation. Meanwhile,
okay.
where did you get this file from? Which folder that you are showing in open this
Yes, sir.
paraview?
Here, tutorial, multi-phase, multi-phase Euler form. Inside that, laminar uh, folder is there, and in that, fluidized bed is given.
Okay. So directly we can open that in paraview.
You were asking for running or
No, no, showing in paraview. I mean, the background my simulation is running. That is
oh,
okay. We have
simulation is
copied
running.
and
Okay,
done
okay,
that.
okay, okay, okay. So, if you want to open it, go to the other or open one more terminal. Okay,
Okay.
in that, go to the same location.
Okay.
Okay, and there you can give paraform. Is it working?
Okay. Let me start
Yes,
it. So that location will be inside my run folder only, right?
yes, 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 yes.
Ah, ah.
Uh, I'm not really sure, sir, because here we are not capturing the any interface. So I don't think so we'll able to use the adaptive mesh refinement for this, because this is like a continuous fluid. Sir, whether you're able to open Paraform?
Yeah, Paraform is open. I mean, Paraview is open,
Okay.
and I have clicked apply. I'm waiting, but
Okay.
everything is looking like empty, just like plain
Because
gray color.
yes, because that is a zero time step. So for that you have to go to this. You have to change the time step from here first. Next frame.
Okay, I have to play it.
Yes, yes. You have to play it, and you have to select any
It
one of
is
this.
running, but still it is that only plain. I mean, I have to change it to, I think,
You have to
some
change.
P or something.
Yes,
U
yes, yes.
air
Yes, U air or alpha particle. Any one of.
alpha particle. Okay,
Yes.
yeah, come on.
Now is it visible?
Yeah, yeah. Thank
Okay.
you.
Okay.
And like meanwhile, my simulation is running. So every time I will run it, it will be updated, I think. Huh?
No, for updating you have to press this refresh.
Okay. Where is this refresh button?
So on the left hand side, if you see this refresh button, you will able to see.
Okay, yes, yes, properties.
Ha.
Okay, okay, refresh.
Yeah.
Okay,
So with
thank
refreshing,
you.
the time step will get updated.
Okay, thank you.
Okay. So these are the two cases for the multi-phase. One in first case we have seen how to capture the interface. In the second phase we have seen how to simulate the two phases using mixture model. So for this also you can perform some post processing, means like how the streamlines are there for each phases. For example, alpha air. So you can see the cliff velocity vector. Scale it down. So this is how you will get the velocity vectors. So any other questions are there?
Could you please show this slice and glyph once again?
Yes, sir. So uh, slice you can do using this option. If you see here the cursor, the slice option is given.
Mm-hmm.
So click over
Mm-hmm.
this slice, then select the Z normal.
Okay.
Okay. So it will give you the plane, a 2D plane.
Okay.
Then switch off this plane. Show plane option is given. You can untick it.
Okay.
Then if you want to see the glyph of air velocity, so select this glyph option. Then scroll down. You can see this orientation,
Mm-hmm.
right? So in orientation, you can select U air, and in the scale array also, you should select U air
Okay.
and then apply. So it will give you some vector. So you can scale it down for better visualization.
You air. Okay. Thank you. Thank you.
Yes. Okay. So mostly for the VOF model, the interform solvers are there, like multi-phase interform is, solvers will be available. And for Euler and Euler modeling, you will get this Euler, some Euler name should will be given. Like I will show you uh, in the multi-phase if you will see. So inside this interform or intermixing form, even this multi-phase interform, these are for the capturing. These are using VOF model for the capturing of interface. And if you go to this multi-phase Euler form, here you will get the Eulerian modeling. Yes, sir. It is from the name of the model. So these were the two cases for the today's session for the multi-phase. So if no further question is there, we can end this session.
Can you elaborate more on the adaptive mesh refinement technique?
Okay. Regarding
That bubble rising case.
okay. So in adaptive mesh refinement, so instead of using a very fine static mesh, so it will only refine near to the interface. So as the bubble will move or it will start rising, it will only capture or it will only start refining near to the interface, not all over the domain. So your overall mesh will be very coarse, but your interface will be very fine as it move upward.
So you have to give other file for that or what?
Yes.
Just like dynamic mesh.
Correct. Just like dynamic mesh, you have to define adaptive mesh also.
Okay. Any tutorial for this case? Where they use
Tutorial,
adaptive mesh.
I think some tutorials are there, but I need to check. Just a minute, I will share it with
Okay.
in this chat box.
Okay. Thank you.
So I think no further. Okay, one question is there.
Okay, so I think we can conclude the session
Yes.
today. Thank you so much. Thanks, Nikhil.